So without further ado, we're going to begin today's presentation. Catherine Duckett is today's speaker. She's trained as an evolutionary etymologist, earning her PhD from Cornell, studying evolutionary etymologist, earning her PhD from Cornell, studying the evolutionary relationships among plant-eating beetles at University of Puerto Rico, Rutgers, and the Smithsonian Institute. She considers climate change to be the biggest evolutionary challenge the world will see in any human lifetime. Her current teaching and scholarly work is the field of climate change and climate change communication, with an emphasis on understanding biological and evolutionary impacts of climate change. Let's please give a warm welcome to Catherine.
Nice applause. Can you hear me?
Yep.
Okay, good. I'm Catherine. I'm an experienced speaker on this topic. So if you don't hear me, raise your hand. If you can't understand something, raise your hand. If you have a question, raise your hand. I'm going to ask you some questions, one, to keep it lively, and also just to make sure that we're kind of on the same page going forward. How many of you know a lot about climate change and what causes climate change?
I think so.
Okay. Well, one of the reasons I ask this is because I've included a little review of basic climate change in this talk. How many of you think that would be welcome? Or
Definitely.
okay. All right. So we have more hands up than there are half the people, so we'll just include that. I can always skip a section if it's boring. Okay? All right. So the topic of this talk, climate change is only an emergency if you are alive, is sort of the thesis of my life now. And one of the other theses of my life now is getting people to see if climate change is an emergency, and if climate change is going to cause untold suffering of humans, animals, and of plants. Plants suffer even though they don't suffer the same way. Ooh, awesome. I usually use a word. And I will trip if I go that way. Is it our personal responsibility to do everything we can to stop or arrest climate change? We can talk about that a little bit more at the end. But this is something that I hold in my own life, that this is a situation that is going to cause much greater, actually greater suffering in the natural world than it's going to cause in the human world, and the human suffering is going to be awesome in the negative use of that term. Okay? All right. So today's roadmap. First, how serious and urgent are the impacts on living systems? But first, some basic climate regulation so that we're all on the same page. Ask questions as needed. And then we're going to talk a little bit about rates of changes and importance to biology, evolution, why these things are actually an emergency. A little bit about ocean acidification and sea level rise, things that are going to impact us in New Jersey, both economically and physically. And then I'd like to have a personal impacts and advocacy conversation because, again, do we have a moral obligation to do what we can? And if what we can is personal or policy, political, all right. We good? Yeah. Good. All right. All right. Given that I talk to a lot of climate deniers, I've phrased this slide this way. The sun controls the Earth's temperature, right? Well, let's walk through how Earth's temperature is actually regulated. Earth gets most of its energy from the sun, incoming solar radiation in watts per square meter. And I'm going to ask you to remember watts per square meter, because this is the unit that the climate scientists talk about energy. And this is the unit that climate scientists talk about warming as generated by greenhouse gases. One of the reasons the Earth isn't freezing is because we have an atmosphere that contains carbon dioxide and water. Water is a greenhouse gas that doesn't last very long, lasts about 7 days. So energy comes in, and some energy is reflected by the surface. And this is a very important thing, because this regulates the ice ages, how much reflective surfaces we have on Earth. If we have more, we're likely to have an ice age. If we're less, we're likely to flip over to a non-ice age. And there's a lot of data, a lot of historical data, geological data, that shows this. Some energy is reflected by clouds. Then you get radiation that's absorbed by the surface, and then you get surface re-radiation. So the light comes in as short-wave radiation, light, and then goes out as long-wave radiation, and it gets recirculated by greenhouse gases. And this shows the energy balance. Are you cool with this graph? Okay? More or less understand it? Okay, good. All right. But what really drives climate? This graph shows various forces that heat and cool climate above and beyond the sun. So you have aerosols from volcanic venting. So in other words, physical particles up in the stratosphere that can reflect sun's energy. And this has been shown to happen after Krakatoa and other volcanoes. There's urban aerosols from pollution. It's warming a little less in China because they've got all that pollution from coal burning. Changes in land use can absorb carbon dioxide. The sun has a solar cycle with sunspots that causes small changes. But most of what's happening here is heat-trapping greenhouse gases. And what are the main greenhouse gases?
Carbon dioxide.
Carbon dioxide, methane.
Carbon dioxide, methane. They're fluorocarbons that are also bad, but they're a lot less. And if you look at the watts per square meter, here we have watts per square meter. It's looking like you've got about 2.5 here, but it's offset with these aerosols from urban pollution at about 0.7. So you're getting a net of what? What's the math on that one? It's about
1.8.
Yeah, about 1.7 or 1.8. So that's what we're talking about in terms of historical levels of what they call historical carbon pollution in the IPCC. Do you guys know what the IPCC is?
No.
Okay, it's the Intergovernmental Panel on Climate Change. And it's important because, as you know, science is a peer-reviewed process, right? You all know that?
Mm-hmm.
And so scientists like me, we go out, we do work, we send it to a journal, the editor looks at it and says, is this good enough to even send out for review? So that's one level of peer review. Sends it out, reviewers. In the Intergovernmental Panel on Climate Change, not only do they look at peer-reviewed publications, but then they have an uber peer review. And in another slide, we'll see some of the IPCC predictions in watts per square meter. All right. Right now, CO2 emissions are rising rapidly. And they're parallel. Temperature is rising, CO2 is rising, and carbon emissions are rising. This slide is actually rather old, but I use it because it has all three of them in one place. If you want to see just carbon dioxide and methane, this is a great figure from the IPCC. And looking at this just from a business perspective, knowing that this is the output from almost 200 years. And this is the output from 200 plus 50 years. What are we expecting to happen in the near future?
Catastrophe?
Yeah, pretty much. That the things we might remember, those of us who are older, who remember beyond 1970, the rate of change appears to be accelerating, right? At the very least, the rate of change appears to be accelerating. So, one of the ways that climate change is predicted is through modeling, right? We can't do an experiment on planet Earth, but we can model different changes. I haven't brought my model slide to this talk because this talk is mostly biology. If you want to talk a little bit later about what the different inputs into a climate model are, I'll show you. But before I talk about this, is everybody clear on how carbon dioxide and methane work as greenhouse gases? Could you explain the mechanism to a kid? Some of you could, most of you could. Are you interested in seeing a little video that shows how it's done?
Sure.
Okay, all right. I'll show you because it's a nice. I found that when I first started with this, I really needed to review how carbon dioxide worked. This is a great little video. It's on your handout.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable negative 18 degrees Celsius. And even deadlier, they range from negative 170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any
This is the fourth
radiated heat.
hydrogen.
But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping into space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
Was that helpful?
Yeah.
Good, good. That's, it's helpful to my students, and I don't want to assume that college graduates are more or less advanced than my students, but sometimes it happens. Okay. So with that baseline, this is a composite of thousands of model runs that the Intergovernmental Panel on Climate Change has done under different representation concentration pathway summaries. And concentration pathways basically means they've constructed different economic and social scenarios with different scenarios of growth, economic growth, population growth, and transition to renewable and clean fuels. Also, some of them I think involve a complete revamp of the economy. But these numbers refer to the number of watts per square meter that each of those concentration pathways will generate. And this is something that's hard to find in the general literature. You'll see these figures and the representation concentration pathways reproduced all over in media. But very rarely does somebody say, the business as usual model, this red line, is going to get us 8.5 watts per square meter more than the historical baseline. Right now, we're at about 1.7. And it's arguable, depending on where you are and what your life has been, whether there have already been impacts of climate change on you. But as you can see, this best scenario is hotter than we are now. That there are a larger number of models run up until 2100, and then some of these models have been run a varying number of times, and this is why the lines don't add up. They don't line up perfectly at 2100. These cones are different model runs, and this is the average of all the model runs. So you were seeing, yeah, as usual, the farther out you get from a base, the larger the cone of uncertainty is. Is everybody cool with that? Mm-hmm. But as you can see, under a business as usual scenario, we're looking at a little bit more than 4 degrees Celsius in 2100. And how many of you have relatives who you expect to be alive in 2100? Yeah, So I kind of care about it, right? That, and at least some of us in this room, well, we might live close to 2100, depending. Anyway, even right now, avoiding 2 degrees Celsius requires this particular representation concentration pathway. And if we're on any other representation concentration pathway, we're getting about 2 degrees Celsius, which is what the wonks at the IPCC say is where we need to be to avoid catastrophic conditions. Later on in the talk, we can discuss how likely it is that we'll avoid catastrophic situations with 2 degrees Celsius. Okay, so why does it matter to us that the world, the Earth is warming? Any ideas?
Because we live here.
Because we live here, right? If we were dead, it wouldn't matter. But biologically speaking, what are the big deals?
Sea level rise.
Okay, there's sea level rise.
Destruction of the ocean.
Drought, famine.
Okay, drought, famine.
Ocean destruction.
Bomb cyclone.
Okay, bomb cyclones.
Mass migration.
Mass migration. Those are all wonderful things. But other than food, they don't really involve other critters. That our economic systems depend on stability and predictability, right? And somebody asked me a question this morning about bees. 1/3 of the food we eat is dependent on bees for pollination. What's going to happen economically if 1/3 of the food is suddenly almost impossible to obtain? Predictability? Stability? So, and current climate has been very, very stable for the last 9,000 years. I've indexed a cartoon that I'm not going to show to this audience, but you might want to look at because it's a great cartoon showing the rise of human civilization and exactly how small the range of climate variation has been during the past 9,000 years. It's a very useful cartoon. Animals and plants can only adapt to change if they have the genetic tools to do so. And that means if their population size is large, or if they have sufficient time to generate mutations. And mutation rate is linked to rate of reproduction. So for certain things like bacteria that have a very fast reproductive rate and large population sizes, they may be able to adapt to climate change. Certain insects, for all that they're small, only reproduce once a year, and they may not be able to adapt to climate change. Larger organisms like gorillas and elephants with very long reproductive periods, and now small populations because of human encroachment, what do you think? It's not happening. And one of the questions I'll put to you morally is, even just as humans, if we take enough pieces of ecosystems out, are we going to be able to depend on what comes out? So the environmental and agricultural impacts of climate change will become unpredictable, and I hope that at sometime in the middle of the talk you'll be with me on that one. Also for humans. Humans evolved about 200,000 years ago. The origins of even our genus are only about 2 million years old. And there really weren't any experience with high carbon dioxide conditions. And carbon dioxide levels that we're expecting outdoors are never going to constitute a danger to human health. But we live often indoors. And if you read the public health literature, there are situations that have been documented in schools where carbon dioxide levels have gotten up to 2,000 parts per million, where significant cognitive deficits occur. And the higher carbon dioxide gets outside, the more difficult it is going to be to control the inside milieu. And under a business as usual situation, we get to almost 1,000 parts per million by 2100. So even for humans, it may start to be difficult living inside. So how does climate change affect ecosystems? And this is like the most boring slide imaginable, but I just want to go through it. The primary climate change issues are global temperature. And later on, I'll show you a situation where some animals drop dead because of the heat this year. Carbon dioxide and other greenhouse gases increase, and these have impacts, especially in aquatic environments, and they may have an impact at high altitude. They certainly have multiple impacts on ocean acidification. They can cause unpredictable weather, and I'll show you later on a situation where this unpredictable weather may affect breeding of an entire population. Species and ecosystems are also experiencing habitat range shifts, timing of biological activities, and different seasonal shifts. This has already been documented in Europe, that birds are arriving to Europe on their regular schedule, and the insects have already gone through their life cycle and they don't have insects to eat. Some people may not care about birds, but they usually care about ticks and mosquitoes, especially ones that carry disease. And birds may need insects to raise their babies in the spring, but if they don't raise their babies in the spring, who's going to be eating the mosquitoes in August? There'll be changes in growth rate that'll be differential. Some, like insects and bacteria, will grow faster, others will grow slower because they'll be under heat stress. This was the case for large mammals. It'll change predator-prey interactions, and we'll talk about this in a minute. Have we had disturbances that are mediated by climate change that have caused drought, fire, or flood in the last 12 months? Yeah. Yeah. And there will be changes in abundance. So these are the sort of the basic ecological changes that climate change will affect. The impacts of warming can be direct or indirect. And in this case, how many of you heard about the flying foxes in January and December that just dropped dead in Australia? 1/3 of an entire species dropped dead out of the trees. That's a selective event. If there's any genetic basis of this, the remaining flying foxes will be more resistant, but there may or may not be any genetic basis.
They don't migrate or anything?
Apparently not.
Or find a cave to go into?
Well, I don't know if there were caves, but, you know, 1/3 of them, that was thousands. In fact, hundreds of thousands. There was another species of possum that also dropped dead in large numbers in Australia this summer in Australia, February.
What was the temperature?
The temperature in Australia peaked at 47 degrees Celsius.
Wow.
There were large areas that got above 44 degrees Celsius. That it got really hot in Australia. That this was caused a couple of years ago by bacteria that thrive at higher temperatures, and it killed 40% of the species of antelope. They just dropped dead. You know, males, females, foals, everybody. Boom. So this is already happening at certain places in the world. We had a red tide in Florida last year that killed fish. The toxins from the red tide killed manatees, and it also wreaked havoc on fish-eating birds, which is why I took this from the Audubon Society. This happened in our country. We had a fish kill in Oceanport because of hot weather out of season very recently. I don't know if any of you saw that, about 2 weeks ago, 3 weeks ago.
What does the term red tide refer to?
Red tide, it refers to a kind of algae. It's a red-brown alga that produces a toxin. It responds very well to warm temperatures. Just like the jellyfish of the Jersey Shore, warm temperatures. So we've also had a problem with kelp forests disappearing in the USA because partially of higher temperatures. And you can see 2008 to 2016, this is a huge biomass. These are forests, they're 200 meters tall. They support everything from sea urchins to sea otters. And they also produce a tremendous amount of oxygen. One little known fact is that 25 to 30% of the oxygen you and I are breathing right now was produced by plankton in the ocean, plankton or other algae. And there have been similar die-offs of algae, large algas, such as kelp, in Australia and Tasmania as well. And guess what? Oxygen levels in the atmosphere are dropping. Not enough to be dangerous to humans at this point. But it's not a good sign. Okay. So, having established that we're already experiencing some biological impacts, I want to talk a little bit about self-reinforcing cycles in the climate system. Carbon dioxide is released from warming water. So the warmer it gets, the more carbon dioxide is going to go into the atmosphere, and the less that's going to stay proportionately in the water. There will always be absorption in water. Right now, oceans have taken up about 90% of the carbon dioxide produced by man. Warming also causes increased evaporation and transpiration by plants. Water is a short-lived greenhouse gas. You know, people say, oh, it's warmer because it's humid and it only feels warmer. Some of it is only feeling warmer, but some of it's actually warmer because carbon dioxide is a better greenhouse gas, but water vapor works really well on the short term, from an hour to a week. We'll talk about this again, but melting ice reduces the Earth's reflectance, or the albedo. And this is very important in regulating the Earth's temperature over time. This is one of those system effects. So if ice melts, even if it's sea ice that doesn't affect sea level, it means that the water will warm. It absorbs about 90% of the incoming solar radiation, rather than reflecting 90% of the solar radiation. You do the math. As sea level rise, more glaciers have their feet in the water. What happens when you put an ice cube in water? It melts. It always melts because there's more heat. Water has an incredibly high specific heat. One of the things we're recently learning also is that meltwater from glaciers lubricate their flow into the ocean, increasing rates of sea level rise. And heat melts permafrost, releasing methane. And methane is a very potent greenhouse gas. It only has a short half-life, between 25 and 100 years, but it oxidizes to carbon dioxide, but it's about 85 times as potent a greenhouse gas. And this is one of the reasons why people will tell you to compost. You think, composting? What does that do for the environment? Well, composting generally means aerobic decomposition in your backyard. So you're generating carbon dioxide from the decomposition of your veggies rather than methane in a landfill. So it keeps away that. Also means you can use the compost to sequester carbon in your own soil.
How does that balance out?
Pardon me?
How does that balance out? I mean, if you're doing your compost for your garden, which is good, but you're creating this.
Actually, it does balance out, because if you put organic matter into a landfill, it's mostly anaerobic decomposition, so it produces methane, which is a much more potent greenhouse gas. So if you're composting at home and you're turning your compost, you're doing it aerobically and you're generating only carbon dioxide. So it's less damaging. It also means that if you're using it on your garden, some of that carbon is going back into the soil, which is the best place for it. Sir?
What's the difference in ratio between that, I mean, what are we currently at, like if everybody composts or?
Well, if everybody, I haven't done the math on everybody composting. But certainly you're avoiding releasing a potent greenhouse gas, a very potent greenhouse gas into the environment. There's no way we can avoid decomposition, but if we can keep it aerobic, we'll put in the fewest amount of carbon. The other thing is waste less. That's actually the first one. Sir?
So what you say is I have to turn over my compost pile.
Yeah, you should turn over your compost pile. You should. That's just good composting. Sorry.
What about leaving grass clippings on the lawn?
That's excellent,
Okay.
because it returns the carbon to the soil.
Yeah.
And most suburban soils are depauperate of carbon. So anything you can do to store carbon on your property is a good thing personally. Everything from planting a tree, etc. Sir?
Can you address the technological efforts to reduce the carbon in the atmosphere, such as the carbon engineering company that started a couple of years ago in British Columbia?
I'll address that at the end of the talk. Is that okay?
Okay.
Okay. Because I want to focus to a certain extent on my area of expertise, which is biology. And this is basic review of your high school. What's an ecosystem? It's an independent system of living organisms, but it's all interconnected. You have fire-mediated regrowth of forests, which will cause different interactions with soil organisms and pollinators and insects that eat new growth versus old growth, insects that eat damaged wood versus not damaged wood. You have plant communities that respond differently to solar radiation and moisture and predation from fish or herbivory. So it's all interconnected, right? And in that way, it's sort of like the climate system. It's a system. It has inputs and outputs and things that regulate it. And we care about ecosystems because we live here, but we also depend on ecosystems for several things.
Food.
Food is one. How many of you like breathing? That one of the things we talked about earlier was breathing, right? That's one of the provisioning services that this particular food web provides with photoplankton. If we were, the water also regulates climate in certain areas. I mean, we wouldn't have such a nice climate here in Red Bank and on the Jersey Shore if it weren't for the Jersey Shore, right? You know, we get all that nice cool season and then it stays warm in the fall. We have that moderating effect. So we like that. We also like the fish. If we were an Eskimo, the cultural services provided by seals and polar bears would be nice, right? How many of you do the Feast of Seven Fishes? No? Nobody here? I guess you're humanists. But the folks you know who do that, if there was oceanic collapse, they would be culturally, it would hurt them culturally more than nutritionally, right? Not to be able to get fish on Christmas? Okay. These are the reasons that that economic systems maybe care about ecosystems. I mean, there are aesthetic reasons for caring that would go under culture. But one of the things I want to focus on is how ecosystems are regulated and how humans have kind of messed with it. And one of the reasons that climate change is putting so much pressure on ecosystems is that humans have messed with almost every ecosystem around. All ecosystems are somewhat limited by the availability of nutrients. In other words, how much plant matter there is and how many mineral nutrients are available to furnish those plants. However, they're also regulated top-down and by predators. And I want to show you a film, if that's okay? Sure. How many of you have seen the George Monbiot film, How Wolves Change Rivers? Okay, well then definitely worth showing if you guys haven't seen it. Because this can say it better than I can say it. And it's really pretty.
One of the most exciting scientific findings of the past half-century has been the discovery of widespread trophic cascades. A trophic cascade is an ecological process which starts at the top of the food chain and tumbles all the way down to the bottom. And the classic example is what happened in the Yellowstone National Park in the United States when wolves were reintroduced in 1995. Now, we all know that wolves kill various species of animals, but perhaps we're slightly less aware that they give life to many others. Before the wolves turned up, they'd been absent for 70 years, but the numbers of deer, because there was nothing to hunt them, had built up and built up in the Yellowstone Park, and despite efforts by humans to control them, they'd managed to reduce much of the vegetation there to almost nothing. They'd just grazed it away. But as soon as the wolves arrived, even though they were few in number, they started to have the most remarkable effects. First, of course, they killed some of the deer, but that wasn't the major thing. Much more significantly, they radically changed the behavior of the deer. The deer started avoiding certain parts of the park, the places where they could be trapped most easily, particularly the valleys and the gorges. And immediately those places started to regenerate. In some areas, the height of the trees quintupled in just 6 years. Bare valley sides quickly became forests of aspen and willow and cottonwood. And as soon as that happened, the birds started moving in. The number of songbirds and migratory birds started to increase greatly. The number of beavers started to increase because beavers like to eat the trees. And beavers, like wolves, are ecosystem engineers. They create niches for other species. And the dams they built in the rivers provided habitat for otters and muskrats and ducks and fish and reptiles and amphibians. The wolves killed coyotes, and as a result of that, the number of rabbits and mice began to rise, which meant more hawks, more weasels, more foxes, more badgers. Ravens and bald eagles came down to feed on the carrion that the wolves had left. Bears fed on it too, and their population began to rise as well, partly also because there were more berries growing on the regenerating shrubs. And the bears reinforced the impact of the wolves by killing some of the calves of the deer. But here's where it gets really interesting. The wolves changed the behavior of the rivers. They began to meander less. There was less erosion. The channels narrowed. More pools formed. More riffle sections, all of which were great for wildlife habitat. The rivers changed in response to the wolves. And the reason was that the regenerating forests stabilized the banks so that they collapsed less often, so that the rivers became more fixed in their course. Similarly, by driving the deer out of some places and the vegetation recovering on the valley sides, there was less soil erosion because the vegetation stabilized that as well. So the wolves, small in number, transformed not just the ecosystem of the Yellowstone National Park, this huge area of land, but also its physical geography.
Put this together. I mean, this is incredible.
Well, some of that research was paid for by your tax dollars, the initial research.
No, but how many scientists put their heads together to figure out that the wolves did it?
That the wolves did it? That I don't know, but it was a few. It was not,
More than a few. More than a few or a few?
well, certainly a few of them noticed it, and then it was more studied, because nobody does anything alone. On my slide here, I show you two, there are two films. One is the one that we just saw. And this one is a very scientific example that is a lot longer, but it goes into it's an ocean regulation example where the first scientists to challenge the idea that all ecosystems were bottom-up regulated went out and did some experiments, and then he found a buddy and did some more experiments. And sir?
I mean, it almost seems like a science fiction story that we just saw. So I'm thinking, like, how many scientists put their heads together and said, yeah, this is how it was done?
Well, it was done by Fish and Wildlife, by reintroducing wolves to Yellowstone,
I mean,
and then somebody studied it. It is mind-boggling, but when you think about New Jersey, how many of you have problems with deer?
Right here, I want some wolves, believe me.
Yeah.
In New Jersey, exactly.
But this is the point I'm trying to make, is that ecosystems are so complicated that we as humans we're not even understanding them all. And right now, we're conducting this huge climate experiment. And what pieces of the puzzle is it going to take out? And what pieces of the puzzle, I mean, the wolves changed the rivers. Okay, nobody would have thought of that. So there are biodiversity generators in every ecosystem, and the ecosystems function together in ways that we don't know. And what can we do to encourage ecosystem stability as we perform this ongoing experiment with planet Earth? I'm trying to make the assertion that basic conservation is also needed because the assaults of humanity on ecosystems have been such that the ongoing assault of climate change may break many of these ecosystems. So even if you care mostly about the effects on people, we need to care a little bit about the effects just on the general environment and doing general things like parks and conservation. However, climate impacts on food webs are of interest just to the kinds of people that you might talk about who are not necessarily interested in other critters for their own sake. There are going to be large impacts on food webs because what we saw about the impacts of the removal and the reintroduction of wolves in Yellowstone. We're removing predators in other places, or they're starving to death. Some of you perhaps have heard about the southern resident orcas in Seattle that are starving to death. And this is a species with a culture. They have a language. It is linguistically different from other orcas. So you could argue that this is genocide, that humans have created an environment where they can't get enough food because they are residents, they're not migrants. And humans are competing with them for salmon, they've dammed streams, they're eating the salmon themselves, they've polluted the environment so there's less salmon, and some of that is from climate change. So this is happening now. However, humans have in the past, by regulation and modifications, fixed what they did. This is a situation in California where there was a marsh that had lost its predators. It had lost its sea otters, mostly because of hunting, and because of that loss plus higher temperatures and these crabs, it was being overgrown by algae. Because the crabs were feeding on the isopods that ate the algae that was growing because it was warmer. Otters were reintroduced and the situation was stabilized, both physically, the marshes recovered physically and stopped silting the bay. So, humans have corrected problems caused by climate change. However, there are other ongoing problems that are quite serious. I'm an entomologist. These two figures from a recently published paper in Proceedings of the National Academy done in 2 places in Puerto Rico. These are the temperature trends in 2 places in Puerto Rico over time. And these are the insects and insect feeding small lizards, anoles, that feed on them in both places. And as you can see, there were abundant arthropods in the 70s and abundant anoles of 3 species And in the 2000s, and this was before Hurricane Maria, the insects have dropped out and the insect feeding anoles are much reduced in number, and there's one species that's completely not there. So these authors attribute this change almost exclusively to temperature, because this area has been a national park since well before that time, and there have not been major land use changes in the immediate periphery. Other authors have reported a worldwide decline in insects, and they attribute this to extensive agriculture and high use of pesticides, insecticides, and herbicides. As you can see, this intensive agriculture, pesticides, and this is a problem for humans, partially because, as I've said before, most birds use insects to feed their babies. And we, like the ecosystem services, of feeding on insects that are pathogenic. Most birds feed their babies on caterpillars in the springtime that they get from plants. If those caterpillars don't exist, there's a problem. But we do have things like ticks year-round. And birds mostly don't feed their babies ticks, but do eat them year-round. And as you can see, under climate change conditions, I believe this is a moderate emission scenario, not a high emission scenario. The area that'll be really, really, really great for Lyme's disease ticks is kind of expanding, and it's going to be a problem. Some of the invasive species that are good habitat for deer ticks are also expanding. They respond very well to warmer conditions here on the East Coast. In the United States, there are many species that are being impacted by climate change. One of the best studied is the American pika, that's dropped out from about a third of its range. It's this little cute critter that lives on mountaintops and eats plants. And because it lives on the top of mountains, it can't really migrate. And it's left it in a very weakened state. So that's one that's affected by the heat. There have been range shifts in butterflies and the birds that eat them documented in Europe. In some cases, the range shift had gone in opposite directions. In some cases, the insects had moved faster than the birds. And in some cases, well, in most cases, that's the case, and it's caused problems in reproduction for the birds. So there's a mismatch. And ecological mismatches between the life cycle of different species that depend on each other is one of the things that ecosystem theory predicts. We've been having this problem in the United States in terms of timing of biological activities. The western bark beetle can get off 3 life cycles rather than 1 in a year now, because usually it's not getting cold enough to kill it off in the winter, and it's warm enough for it to have many life cycles. And as you might imagine, if an insect has 100 babies in the first generation, if it gets a second generation, each one of those 100 babies has 100 babies. If it gets a third generation, we're talking big numbers. This is also a problem in the pine barrens. And our recent fire was partially due to dead wood from bark beetles. So here in New Jersey, we're also having climate-mediated issues with insects. We're also having climate-mediated issues with big storms, and these cause problems for critters. This is a small island off the coast of Hawaii that this is before the hurricane, and this is after the hurricane. And as you can see, it's a small island. there's nothing really left of it. Why is this important? The Hawaiian monk seal is an endangered species. That was one of their major breeding grounds. I don't know how smart the Hawaiian monk seal is in order to find other breeding grounds, but the ones that really went here are SOL. Okay, but the big problem in marine life with carbon dioxide is something that not related to heat. It's ocean acidification. This is a pteropod. This is salmon food. This is a small pelagic mollusk. You can see the shell here, or can you see the shell? Okay. Anyway, as atmospheric CO2 goes up, dissolved CO2 also goes up, and pH goes down. And pH is a logarithmic scale. And at this point, seawater is 1/3 more acid than it was when I was born, 50-odd years ago. And is this a problem? This is a problem. This is a pteropod shell. This is how it looks under conditions of ocean acidification, and this is how it's supposed to look. So pteropods are spending more energy putting calcium back into their shell that they're losing from slightly acidic waters. It's keeping them from growing and reproducing. And this has potential food web impacts. Salmon eat copepods and pteropods. Coccolithophores are also calcifying creatures. They make up the basis, their calcium skeletons make up the basis of chalk. Have you ever been to Dover? White Cliffs of Dover are coccolithophore skeletons from long ago. It's a kind of plankton, photosynthetic plankton. But it's the base of the Pacific salmon food chain. They're also having trouble maintaining their skeleton at current levels of ocean acidity. They're able to, but they're spending more energy doing so. And this slide from marine fisheries in the Pacific shows the pink salmon diet. It's mostly pteropods. And what they found is that a 10% increase in water temperature will cause a 3% drop in salmon weight. But even more, 10% decrease in pteropods will cause a 20% drop in mature salmon weight. And salmon are the base of the food chain out there. Certainly orcas, seals, humans all need salmon. So right now, there's a distinct physiological effect on pteropods that we can trace into salmon. We can also trace acidification to an oyster emergency. Under the Pacific Oscillation, what we know as El Nino, Southern Oscillation, there are times when you get distinct upwelling of acid waters on the Pacific Northwest. And oyster farmers have found that they cannot get the oyster larvae to convert to small oysters during those times. So they have to monitor the water, and during those times of acidification, they have to bring in the oysters, have them reproduce in a lab, de-acidify the waters with lime until the little oysters can convert to a shelled critter, and then they can put them back. How much do you think that affects their profit margin? Yeah, wow. And I'll remind you that scallops are a $1 billion industry in New Jersey. We haven't had the problems with upwelling and acidification that they've had in the Pacific Northwest. But are you going to take my bet that it's coming? Nobody's going to take my bet that that's not coming. And so these both have marine mammal impacts. We've already discussed the orcas that are starving to death. But walruses depend on both sea ice for secure places to haul out, but they also eat mollusks. So their populations are dropping because of lack of sea ice and just drowning, but they're also going to be dropping because of the lack of mollusks. That lack of mollusks will also affect skates, and there's a fisheries in skates. So you guys, you don't need me to draw you the diagram, right? You're good. All right. So this is a slide that just sort of summarizes all the documented problems with ocean acidification in marine organisms and marine ecosystems. And I'll point you to the ones in fish. Fish have a problem with sound absorption, homing ability, and avoiding predators for many of them as larval fish in high acidity conditions. Some of those conditions do exist on the Jersey Shore. There's a big effect also on juveniles and larvae, as we've discussed. This is a slide from the UN, which discusses the economic impacts of ocean acidification on various fisheries. Finfish, as you can see, are a huge industry. Coral reefs provide a nursery. And what's the news from coral reefs?
They're dying.
Yeah, they're dying. You know, this is sort of a boring story, right?
No.
I mean, it's the same old thing. It's a scary story. And these effects are morally important because these creatures have a right to life, but they're also significant because can we support an ever-growing population with less food that's provisioned by the ocean or the land that's otherwise free? And especially if we start having an oxygen problem. Okay. In New Jersey, people always want to talk about sea level rise, and I'm getting sort of towards the end. So bear with me. Sea level is rising in New Jersey for two reasons. One is sea level's rising. The other is the land is sinking. Do you know why the land is sinking here in New Jersey?
Taking the groundwater out.
That's one reason. But the biggest reason is actually isostatic rebound. Because New Jersey was very close to the end of a glacier. The glaciers basically ended at right up here in the Raritan River, and New York, Staten Island being a terminal moraine in parts of Atlantic Highlands. The Earth crust is a very solid gel, but it will act like a gel. When there was a rebound after the glaciers melted, and then we bounced down again, and we're bounced up again, and now we're bouncing down again. So we're going to lose about 5 inches in New Jersey that other places aren't going to lose. So New Jersey is going to have a little more sea level rise than others because of that isostatic bounce. But the other reason is a really cool reason we're going to have more sea level rise, and it's gravity. I will point you to this picture of a pseudo Antarctica or Greenland. There's so much ice on both Antarctica and Greenland that it has its own gravitational pull. And right now, the gravitational pull is diminishing because Greenland and Antarctica are melting. And because we're further from Antarctica, as Antarctica melts, sea levels are going to slosh more our way because the gravitational pull of Antarctica towards Antarctica will lower sea levels near Antarctica. And the pull of Greenland isn't as big. I also wanted to show you this, that one of the reasons sea level is going to rise is because sea levels are rising. And most of Antarctica and Greenland, or at least large parts of Antarctica and Greenland, are underwater, or below sea level. So as sea level rises, that water is touching the base of the glacier, helping lubricate it and run to this ocean. But it's also going to go over the lip of the bowl, and then there's going to be a whole bunch of ice with its feet in the water.
Yeah.
And that's a poorly known fact. This is the map of Antarctica, and as you can see, below sea level are these large areas, very large areas of West Antarctic Peninsula, West Antarctica, and there's some areas of East Antarctica that are below sea level. An even more important point to note about Antarctica is that for most of our lifetime, Antarctica has been contributing trivial amounts to sea level rise. But since 2005, when the contribution of Antarctica to sea level rise was a couple of millimeters, the contribution has more than doubled. It's accelerating. And weather conditions are such in Antarctica that Antarctica was growing for a while and it's not growing anymore. And there is no modeling that indicates that that trend is going to reverse itself. As a matter of fact, current research on Greenland geography have indicated that this fjord here is much, much deeper than previously thought. There have been, in geological history, several times when Antarctica has collapsed, and that there's been rapid sea level rise. Antarctica has about 200 feet of sea level rise wrapped up in it. So the last time Antarctica was melted, the sea level was so high that, you know, that part of Route 18 in Old Bridge where Route 18 goes up, that was where the coast was. Yeah, exactly. So they had not understood the mechanism of how that ice would collapse because they didn't understand how deep this fjord was. And they've done some more studies on the physics of ice, so they know how high an ice cliff will be without collapsing under its own weight. And many of these areas are taller than that. They will collapse rapidly under their own weight. So there are several models out now of sea level rise that do not incorporate Antarctic collapse, and there are other ones that do. And I'll show you some of those in discussion time if we have time. But remember the self-reinforcing cycles I talked about, and this is why this is going faster. The water around both Greenland and Antarctica is warming, and it's getting into some of these areas that are where huge ice cliffs have their feet in the water. Okay. All right. And of course, in terms of economic stability and security, these are large population areas that are very close to sea level. And most of Bangladesh is very close to sea level. The mass migration problem, because of sea level, is going to be an issue. Okay, what can you do? There are a number of basic things that you can do, and I recommend all of them, although the one that I recommend the most may be a surprise to you. You can reduce your carbon emissions in a variety of ways. You can sequester carbon. We've been talking about habitat stabilization. This is my front yard, which I have created a sort of a haven for nature with native plants, mostly as a showpiece, but to support native insects that support native ecosystems. But you can change the conversation nationally and locally. And I know you guys are going to be having a Green New Deal conversation, right? Okay. So there are all kinds of personal choices that you can make to reduce your contribution to climate change. And some of them involve charitable giving, and some of them involve avoid one round trip transatlantic flight. That's like one of the biggest ones you can do without giving up having children. But I will say that I was talking to a group of mostly grandparents, and I was speaking with a young woman who was of childbearing age, and I told the people who were of the right age to be grandparents, stop pressuring your kids to give me grandkids. And the expression on my co-presenter's face was just of such relief. She was like, oh my God, somebody understands me. So social pressure, forget about it, you know, try to support the kids that your kids want to have. But these are all relatively small things. To really make an impact, you've got to walk the walk yourself. I mean, I'm not vegan, but I've cut down my meat. I put on solar panels. I walk to work. I did drive here. But we have to work together to really change the system. I mean, and you've seen ecosystems can be regulated in surprising ways. We're in an economic system. We need to consider what are the leverage points in our economic and political system. And I'm doing this in my town. I'm doing this in my town. I'm talking to public officials every time I can about carbon tax. Menendez didn't really want me to ask him about a carbon tax when I shook his hand last time, but I did. But one of the things you can do that has the most impact is actually talk to people. And why do I say this? Americans agree that climate change is happening. These are maps from the Yale Center for Climate Communication. And as you can see, most people feel that climate change is happening. The hotter colors are more, the cooler colors are fewer. The estimated percentage that adults think global warming is caused by human activities is a little low. So that's an inflection point where you could at least tell people that you accept that science. And even if you only ask for beer with the lower carbon footprint at the liquor store, you're still communicating to somebody that you think this is important. There are lots of ways to talk about it. However, most people don't ever have a conversation about climate change. As you can see, this is a really cool color. Most people don't talk about climate change, but they do think that we should fund research into renewable energy. That's another thing to talk about. People agree that renewable energy is good, they never talk about climate change. The percent of adults that think that Congress should do more to address global warming is also in the warm colors. It may not be as warm as we'd like it, but so that's something to talk about. Is it really, and it's all of our jobs because this is an additive issue, but Congress has a big job to make the world better. Do you follow me? Okay, all right. And at this time, I will stop for questions.